Let f be a function with domain V. We say that... Notice that I cheated in the definition of a linear function. Let f be a function with domain V. I never defined its domain and just left it as a V. Function with domain V, domain V.
Domain V.
If you take Stanford's algebra courses Math 113 and Math 121, or Stanford's General Analysis course Math 171, you will learn that V is an abstract collection known as a vector space. For example, suppose V is the set of differentiable functions. Then the derivative is a linear function on V. The derivative of the sum of two functions is just the sum of the individual derivatives. The derivative of f plus g is the derivative of f plus the derivative of g for all differentiable functions f and g. You can always pull a scalar out of a derivative. The derivative of alpha f is the same as alpha times the derivative of f for all real alpha and functions f. Likewise, if V is the set of integrable functions, the integral is linear on V. But for this course, we're gonna assume V is a subset of Rn. Moreover, we require V to have certain properties. Recall that our definition of a linear function took V to be the domain of f. Fx plus y equal fx plus fy. The property only makes sense if the domain is closed under addition. If x and y are in V, then so is x plus y. Also, alpha fx equals f of alpha x only makes sense if the domain is closed under scaling. If x is in V, so is alpha x. This motivates us to make the following definition for such a domain V. Definition. A subspace is a subset V contained in Rn that satisfies the following properties. Existence of zero. The zero vector is in V. Closure under addition. Given two vectors in V, their sum is also in V. X plus y is in V for all x and y in V. Closure under scalar multiplication. For any vector, all scalar multiples of that vector are in V. Alpha x is in V for all x in V and real alpha. One question you may be asking yourself is, why the existence of zero requirement? In particular, one could make the following argument.
If x is in V, then we immediately know minus x is in V since V is closed under scaling. But if x is in V and minus x is in V, x plus minus x is in V by closure under addition. Hence, 0 is in V. So this means that the existence of zero requirement is redundant. Piggy!
For a frog, this argument isn't half bad. However, there is a slight fly in the ointment. How do we know there is actually some vector x and y in V? it's entirely possible that V contains no vectors. Remember our mantra?
Math mantra! Don't forget to check degenerate cases!
And the empty set is the most degenerate case of them all. So the only real purpose of the existence of zero requirement is to forbid the empty set from being a subspace.